Hello, good morning or good afternoon, good evening. Just waiting for a few more people to join. Hi, Jing.
Hey, Alex.
Do we have the Xline project team on the call?
Yes, we're online, Alex.
Fantastic. Thank you for joining. We'll probably wait maybe one more minute. Jing, what do you think?
Yeah, sounds good.
Okay. How about it? Shall we start? And then
Yeah.
if other people join, we can catch them up.
Yes,
Um,
sure.
So for the Xline team, welcome to the storage tag. We would love to hear more about the project. Do you have some slides that you want to present?
Yes, we have a slide to share.
So before we start, I just spend a couple minutes on the white paper? I just want to.
Yes, okay.
Let's see. Basically, the draft is out. Just to ask everyone, please review it. Another thing I was thinking, maybe we need to add some diagrams because right now the paper doesn't really have any diagrams. So if there is any volunteer to help with that, let us know.
I can try and have a go this weekend. That would be good. Agreed.
Yeah, sure. Sounds good. All right. Okay, that's all I want to say about the white paper. Yeah, excellent team, please go ahead.
Okay, wait a minute. Let me share the slide. can you see the slides?
Yes.
We can do.
Can you also put the link in the agenda doc? Is this, I'm not sure if this is, if you have a shareable link, or you can do that later. You can do that
Okay,
later.
I will do later. Do you mean the link to the site?
Yeah, the link with the slides, if you can, we can add that to the agenda doc, that'd be great.
Okay. I can send you the slides after the meeting. Yeah.
Okay, sounds good. Thank you.
Yeah. Okay, let's start. Hello, everyone. I'm very glad today to introduce the open source system Xline. First, let me introduce myself. I'm Ji Chen Shi, and I'm the co-founder and CTO of a startup company named Data Lord, who focus on providing storage solutions for sky computing.
Welcome.
It's the first time we introduce a Xline system, so I will talk about the background and the motivation of this project and the problem it's trying to solve. Then we will introduce the system itself, named the Xline, which is a geo-distributed metadata management system. Cloud computing is nothing new today, but sky computing is not that popular nowadays. For simplicity, let's say sky computing is building bridges between cloud vendors and many private clouds. Yes, it doesn't mean servers located in different data centers can't talk to each other, but it's not efficient considering the network latency. Currently, migrating a computing itself is quite easy, as pulling an image is fast for containers. But moving data is another story. So that's why we built Xline, the KV store, to address this issue. Then let's see how today's metadata management systems work and their limitations. Later, I will talk the root cause of it, which is the underlying consensus protocol. Nowadays, popular metadata management systems are almost distributed, just like etcd. Then the communication between server nodes are not a big deal if they locate in the same cluster. But the situation changes when it comes to multi-cluster or multi-clouds. The communication latency is up to hundreds of milliseconds. The round trip time becomes the largest bottleneck of the system. Then let's see how to deploy etcd in such a scenario. First, we can deploy all the etcd node in the same cluster. It works fine. Every request from the same cluster get a quick response. But at the same time, all the requests from outside have to suffer the long latency, even it's a quick read operation. Besides that, this deployment can't tolerate a cluster level failure. Yes, people say there's no cluster level failure in the real world. Every data center has backup power supply, and it's not possible for servers in a single cluster fail at the same time. But network misconfiguration may easily cut down the connection from the cluster to the outside. In that case, all servers in this cluster is down for the outside world. It's already happened before. So it's not a good way to deploy etcd in this way. So let's see if we can do it better. Then we can try another deployment method. This time we put every server node in a cluster. So every cluster has a local etc server. A faster read is possible. But for the write operations, the situation is worse. Most requests suffer 2 times latency. To explain the reason, let's see the protocol underlying the etcd. It's called the Raft consensus protocol. Just like what's shown in the left diagram, the client sends a request to the leader. then the leader broadcasts to the request to all the followers. Once it gets enough OK response, it tells the client that the message is committed. There are two round trips, which is shown in the right diagram. The first is comes from the client to the leader. The second comes from the leader to all the followers. Now we can see that in the geo-distributed system, the normal consensus protocol, for example, Raft, doesn't work well. Then we build a system named X-Line to try to replace etcd in the geo-distributed scenario. Here is the architecture of the system. Every request sent to the server will process by the request route to determine whether it should be duplicated to other followers or not. If the answer is yes, then the request will be passed to the consensus protocol. After making sure it's being committed, the system will check oaths and run the request in the command engine, and the state change will be saved in the storage engine. The engine can be in-memory engine or persistent engine like RocksDB or something similar. The main innovation of the system is a consensus protocol. This protocol is called CURP. The protocol is first published in 2019 on NSCI. The main idea of the protocol is to separate the durability and the global ordering. So what is durability? It means every committed request doesn't get lost when the majority of the servers are alive. Then the global ordering means that every command is executed in the same order for all the servers. Couple protocol achieve both goals by a two-layer design. The left one and the right one. The front layer shows here is called speculative pool. It's used to make sure the durability. The backend layer makes sure the durability and the ordering at the same time. For simplicity, the Raft protocol itself is a good backend layer. The main difference between the CURP and other protocols is that the client sends requests to all the servers instead of the leader only. In the most cases, the protocol can be done in one RTT. But the benefit is not free. We need to provide additional information telling whether two requests conflict with each other. If the answer is yes, at least one of them must be passed to the backend layer. For example, the Raft protocol before the server responds to the client. We can see that the more confliction will lead to the worst performance. In the KV store case, it means that if every request are modifying the same keys value, it's a worst case. The performance degrades to the Raft level. Okay, that's the main idea behind the CURP protocol. And to make the user migration easier, we make our API compatible with etcd. Currently, we've spotted as data-related APIs. Others are under development. If you want, the current etcd client can talk to the X-Line servers directly. We have tested to make sure it works. But if the user want to get the better performance, the etcd client or SDK is not a best choice. We can see in the left diagram, it still takes 2 round trips to finish a request. But instead, we recommend our X-Line SDK. Only with this SDK, one round trip message passing is possible. To verify, yeah.
Could I ask a quick question? If you go back one slide, so with the CURP protocol, does the client take responsibility for making sure that each of the servers has responded? So I kind of get that the client is going out in parallel to the different servers, but is it the client's responsibility to ensure that enough responses have come back?
Okay.
To,
Okay, it comes to the detail of the CUP protocol. The client will send a request to every server. And if the server accepts the request, it will tell the client, yes, we accept it. Then if enough OK response get, the client knows, OK, the request is committed. We can do the next request. And the server in the backend, it will go from the front end layer to the backend layer and do the other things.
right, but then does that mean that the client has to be responsible for like doing, say, a rollback of the commit if it doesn't get enough OKs back?
No, it's not the client's responsibility. There is still a leader on the server side. If there's not enough OK comes from all the servers, the leader will take the responsibility to make everyone, the average followers committed to one request, and then send back the response to the client side.
But
Okay.
the question is in is X-line, is that how you call it, or Xline? How do you call it? How do you call this program? Is it X-line?
So sorry,
It is, yes. It's
Okay.
The product's called Xline.
Excellent. So in Xline, on the right side, server 1, server 2, and server 3, according to the proposal, those are geographically or far away from each other, further
Yes.
than the servers on the left side, because in etcd it's normally done in a single cluster. But the whole point of Xline is to say that you have them at a larger latency between the servers. Is that correct?
Yes.
So would that mean that then the client communicating through the CURP request protocol or even the etcd protocol would have to wait longer, because it's going to wait for much larger latencies, right, as it goes across, unless there's something I'm missing. Am I missing something?
Yeah. The left side is how etcd SDK does. First, it sends a request to the leader, and the leader
Yes.
broadcasts the message to other followers. Then
Yes, this is
follow
Xline backend. That's why it's using CURP.
Yes, it's it works the way if you use the etcd SDK.
Sure. I'm not my really question is it's more like the goal of the project is like, if the servers are geographically further away so that latency is higher,
Yeah.
then the client, what is the client affect through this change? What's the benefit of Xline here? I don't see it. I still see the request taking a long time. Now, they're in parallel, right?
So Lewis, I think you might have missed a couple of the first slides, but I think, and Zhisheng, correct me if I'm wrong, I think the concept here is with etcd, the client sends a request to the leader, and then the leader has to go through a commit process to get the followers to commit as well, and then the leader responds to the client, which basically means you have a minimum of 2 round trips. And of course, if the servers are geographically located, 2 round trips is very expensive.
Sure.
The CURP protocol is kind of changing it so that the client goes out to all the servers in parallel, so that effectively you only have 1 round trip, and therefore you're kind of halving the latency in when the servers are geographically located.
Yes.
So you have 1 run trip. So the client is almost like a participant in the cluster. Yes.
Yeah, the client gets some intelligence, I guess, from this.
Yeah. and the client would need to know, this is exactly the difference between Ceph and GlusterFS as a replication model, okay?
Yeah.
The one on the right is the GlusterFS. It replicates from the client. And the one on the left is Ceph, which replicates at the server, right?
Yep.
So
Yep.
there was pluses and minuses to both. On the right side, you divide your bandwidth in thirds, according to this, because now you're dividing your work in the TCP depending on going back and forth. And also your client has to have the information of all the servers, right,
Yes.
that are available.
Yes, I think the big idea is similar, but the Cooper protocol also takes the responsibility of the consensus to make everything on the same page, not only duplicate the request.
Sure, I understand. I understand where you're going. Continue.
Yeah.
So can I just understand that like the X-Line SDK is just a multi-threaded parallel version of the ETC SDK?
It's not the same. It's not same. It changes the way it talks to the server. So it's not another multi-threaded version. The protocol itself is totally different.
Okay.
Yes. So let's continue. Yeah, to verify or demonstrate X-Line really has bad performance in geo-distributed scenario, we build a test environment like the diagram here, simulating the network latency in the real world. Every message takes about 100 milliseconds to finish a round trip. And here is a result. And just like what we said before, if all the clients try to modify and read a single case value, it's the worst case. Performance is similar to etcd because it runs a router in the backend part. So, but if we make the key space larger, X-Line throughput is as twice as etcd because it takes only one round trip instead of two in most cases. The performance result here is taken on the memory storage engine. Recently, we released a version 0.3, which supports persistent storage, which means every request or command will be stored on the disk. The test result keeps the same. It's not hard to predict for that the network is a bottleneck of a geo-distributed system instead of disk itself, right? Then here is our roadmap. We started the project from last year, and we keep updating features since then, and plan to release a stable version next year. At that time, it should be a stable and reliable metadata system for the cloud-native apps. The top right corner shows the project link, and yeah, that's all I want to share today. Thanks for your time.
Thank you for the presentation. I did have maybe a few more clarification questions on the CURP protocol and its implementation. So,
okay, let's go back.
So for example, how do we maintain consistency when you have a scenario that different clients can see different servers? So for example, if client 1 can see server 1 and 2, and client 2 can only see server 3.
Okay, I see.
Like if client 1 does a put, how does client 2 do the get if server 3 might not have received the data, for example?
Yeah, maybe I didn't make it clear. The client of X-Line will send requests to all the servers. It will not like intelligent pick 1 or 2 servers. It will try to talk to everyone, and it will try to get enough response from the server. usually the super majority of the server.
Right, right. But take this as an example, right? So
Yeah.
so say the client can't talk to server 3 because of a network partition, for example,
Mhm.
but it can talk to server 1 and server 2.
Mhm.
So it sends the request to server 1 and server 2,
Mhm.
and because there's a majority that's committed,
Mhm.
how does server 3 receive the data? How
Yeah.
does server 3 become in sync?
Here's the graph. We can see from here. At the top is server 1, server 2, server 3, right? The message is sent to the server 1 and the server 2, but not sent to server 3. And the server 1 is the leader. The backend protocol will try to broadcast the message to the other followers. So finally, server 3 will get the result.
I see.
If there were only two, this could create, if client only sees server 1 and server 2 is broken, the connection is broken, and then this create a split brain situation where it doesn't know who, I mean, I guess the leader always knows it's my data, but if the client is connected not to the leader, like if it's connected to server 2 and the leader is server 1, I just gotta be honest, it's creating or having the client participate in the cluster synchronization and leadership is tough. It brings in a lot of issues. So
Yeah, you mean how client to gather information who is a leader server, and
yes,
how it handles if the leader changes, right? The leader information is maintained in another metadata information server, and you can get the server's information from that metadata server, and that server is used in, for example, to if you want to join a new server in a cluster or remove one from the cluster.
okay, I understand. If I had to suggest is
Yeah.
that you make something else the client understanding this whole world and have the actual clients be dumb. In other words, have something in between the client and this system you're creating, which understands if a new node came in, new clusters came in and added to the cluster, or some got removed or something happened, it manages that. But having it at the client, when you have hundreds and hundreds and thousands of clients, it could really cause a situation where they don't all have the data of the status of the cluster correct, right?
Mm-hmm.
So
your question is, if the number of clients is really large, it will hard to make the client get the latest information.
yes, at some point you will run just statistically, you will not have all the data in all the clients, all the status, right?
Yeah.
And so what I'm suggesting is have an encapsulation, something that understands the cluster, and if it is like a client, like you have it here, but then the clients become dumb, right? So
the client can talk to that service. That service information is always up to date.
Okay.
And yeah, client not always talk to that server. It can talk to all the data server directly. If it can find it cannot talk to the leader directly, then it will fall back to retry logic, like to try to fetch the latest metadata, who is a leader, and maybe I will need to change my local server configuration, talk to a new leader or something new, right?
Yeah, again, it can be done, but it's tough because now the client has to say, oh, my leader's gone, I need to know who I can talk to now, or you may have to go to somewhere else to get a directory service to understand who is the next server that can talk to. I don't know.
It may be an optimized, like if you talk to server 2, it says server 1 is no longer the leader. You can
exactly.
Yeah, it's a way to optimize it. Yeah. Thank you.
Well, kind of following on your thought there, Louis, is let's say your cluster went from 3 servers to 7.
3 servers to 7.
7. And so the client in the old state thought that a response from 2 servers was good enough. And so you have a synchronization as you grow, because there's a secret that both sides are understanding is the size of the cluster, which I think is kind of where Louis was at, is that they both have to work understanding who's the leader and what's the size, so the client can make the speculative decision. So so is there part of the response that says our cluster has changed, or we are now at a cluster size of 6 or 7? Excuse me, I gave the wrong example.
Yes, 7. You mean the client takes some. Client must know what happens to the cluster. For example, the leader change, the size of the size of the cluster change, right? Because every time the leader change, for example, if we use the backend, the protocol, uses the Raptor protocol, it had a number to indicate the epoch. We can tell if there is a change in the cluster. If the epoch number increase, we know something happens to a cluster. We must to fetch the latest data.
Okay, so the COOP request starts off with an epoch number. The server changed while in flight, and the response comes back with a different epoch number, and the client knows to retry or get fresh state. Is that what I heard?
If it gets a different epoch number, it will. If the number of the leader is get smaller, means maybe it's not the latest leader. It needs to fetch the information of the latest leader, or if the number is larger than what we stored locally, it means maybe the cluster size changes. It may add new servers to the cluster. We need to fetch the new data from another metadata server to refresh the information.
Thank you.
Well, when you're talking about another metadata store, is it part of the same cluster, or is it another cluster?
It can be anywhere. If you want to get a better performance, you can place the server on the same server of this data servers.
So in a scenario where you're using Xline with the etcd SDK or the SDK the etcd API, what would the advantage of using Xline be over etcd? Because obviously you don't get some of the latency advantages because of the protocol, right?
Yes, if you use etcd SDK, it works almost the same as etcd. So we do it only for compatibility. If you user don't want to change the code or something. If you want to get to the best performance, you have to do some code change. We have to do our best to make the code change small, to make the API similar.
Right. And when you're using the etcd SDK, you are effectively always talking to the leader, right?
Yeah, the later. Yeah.
Okay. Do you have any information about how Xline stores data on like how it persists the data? Because it occurs to me that aside from the protocol enhancements here, it could be, one of the challenges with etcd is always how do you scale it in terms of, the number of objects and things like that. And I'm kind of thinking this could be an interesting way of providing like almost like an alternative to etcd for scale out number of objects.
Currently, we use RocksDB to as a backend of the persistent storage. So every time we want to save the data to the disk, we call the RocksDB's API. Yeah, so we rely on that system. Yeah.
Isn't that the same that what etcd is using?
etcd is using both DB, I think.
Oh, okay, right. Okay.
That's interesting. Certainly Rocks is possibly more scalable in that respect.
So if some user want to migrate from, let's say, etcd to Xline, are there any challenges?
Yeah, if the user just want to have a test to make sure our system really works, it can just start up a Xline server cluster and use the original etcd client to talk to our servers. Yeah, if user really want to get the better performance, they have to do some code change to change the way it talks to the backend servers. But yeah, the detail is hidden by the SDK. So the user level or the programmer level code API is almost the same.
Okay.
Good.
Yeah,
Is it mature enough to be used for, to provide etcd for Kubernetes, for example? Does
we
it have the
haven't
functionality?
We haven't tested that, but we are planning to do some test to, for example, to change the etcd SDK in the Kubernetes to see if it works in our system.
Interesting. And of course, if it ever gets to use the Xline SDK, then
yeah,
you could have like a stretched Kubernetes cluster potentially.
Mm-hmm.
What is the status of this product currently? Is this you're using this in production or you're still in testing phase?
Yeah, we are still actively developing it, and it's not that stable yet. So yeah, so I think we can make it stable the next year. Yeah, we also want to introduce the chaos engineering to the to validate our system to make sure it really stay stable.
Is the 1.0 out, or is this, I see this 2023? This is still in progress, version 1.0.
2023, yeah, it's still in progress. We have done the persistent storage, and we are now doing the snapshot. We are going to release the new snapshot version this week. Yeah.
Okay.
Well, this is very interesting, and the plan is to submit this for Sandbox.
Yeah, we are submitting it to Sandbox.
Brilliant. Well, it's very, very interesting. Thank you for taking the time to present to the community.
Thank you.
Yeah, thank you very much.
Is there any other questions for Xinjiang?
Yeah,
Did I
just
pronounce your name correctly, by the way? I hope I didn't mispronounce your name. Sorry. Sorry, go on, Tom.
I just sense of other people in the community who have kind of joined you in wanting to solve this. Do you have a critical mass of colleagues working with you?
You critical mass. You mean have you validated the protocol or something?
No, I'm sorry for my colloquialism. Are there other developers of other communities working with you, or is the development team pretty much all within your company right now?
Yeah, we have some outside contributors, but now the contributor is not the contributors number is not too large.
Roughly
That's
how
where
many?
everybody's-
6 or 7. Yeah.
Yeah, I just see 8 contributors listed on your GitHub right now.
Yeah, 8. Oh, okay.
And also because it looks like you just added this in the GitHub not too long ago, right? So your first release was not too long ago, I believe.
Yeah,
last year. It's very new.
Yeah, yeah. The first release is not too much earlier because we started the project just from last year.
Okay. And so you have this issue opened to apply for CNCF Sandbox. So basically you are waiting for the next round of voting, right?
Yes.
I see this as submitted in November last year.
Yeah, it's submitted last year, but it should be reviewed in the last meeting. But we are the fifth project in the list. Last time the meeting just reviewed 4 of them. So
I see.
A question, since I've got all this expert on storage, I'm a traditional monolith database guy. So running on database on Kubernetes, some of the implementation at least depend on the stability and reliability, everything about etcd. So I mean, is there any remaining things to look into to make sure that to run database on Kubernetes, anything else need to be resolved before it's fully reliable?
So if you don't make the run, your question is how do we make our system reliable, just like etcd works?
For example, some of the database implementation use etcd as a catalog for the database node running on the cluster. So yeah, not specific for just for Xline, but also etcd. Is there anything else that's being worked on to yeah, because it just makes me think of one database integrity depend on the integrity of another database. That's just a kind of question mark for me.
Yeah, I think we first need to make sure one component is stable enough. For example, if you depend on etcd, you must make sure the etcd is stable. If it's not, it's really hard to build a stable system based on another unstable one. So sorry, maybe I didn't get the point.
Yeah, I'm just relatively new to the whole Kubernetes world, so I guess I need to understand etcd more.
Okay. Are there any other questions from the team? All right. Fantastic. Thank you again for the presentation, and I hope we get through on the sandbox. Jing, did we have anything else for today's session?
Well, it's just this white paper which I mentioned a little bit earlier. We can, let's see, maybe we can just go back there. Let's take another look. Right, so we have this link for our DOK white paper. Just need to get more reviews, and then hopefully we can finalize this and get it published. Yeah, adding some diagrams will be great. So Alex, you'll be taking a look of this.
Yeah, I'll have a look at that.
Yeah, that'd be great. Yeah. Yeah, that's all. I don't have anything else.
Good stuff. Well, in that case, we give everybody 10 minutes back. Thank you for your time today.
Yeah, hey, thank you for the excellent team for your presentation. That's great.
Thank you.
All right.
Thank you.
Have a good rest of your day.
Thank you.
Bye-bye.
Bye-bye.